Welcome to Lecture Online. Here's our second example of how to find the Fourier series of a periodic function. It's a little different than the one we did in the previous video. Notice that here we have a magnitude of +1 between 0 and 1 and a magnitude of -1. I write it down, but let's write down -1 when we go from 1 to 2. Again, the period is from 0 to 2, so period is 2 units long. The frequency is 1/2, and omega, the angular frequency, is 2 pi f, or equal to pi. This is the equation that we use to find the Fourier series of the original periodic function f of t, and it comes down to finding the a sub naught, the a sub n, and the b sub n. So what do we do here now when we have the value of the function is equal to 1 from 0 to 1 and -1 from 1 to 2? Well, later on we'll learn some techniques where we can simplify the problem. Right now what we're going to do is simply make two integrals, one that goes from 0 to 1 and one that goes from 1 to 2, because the value of the function is different. Later on we'll see that this is an odd function, and so therefore there's some rules that we can use to simplify the problem. Now what we're going to do is we're going to start by finding a sub 0. So in other words, a sub 0 is equal to 1/t times the integral from 0 to 1, because we're first going to start with this portion right here, of the function, which in this case will be 1, times dt. And then we have to add to that, so let me put a bracket around it, add to that the integral from 1 to 2 of -1 times dt. So we have to account for both portions of the period. The closing bracket here, so this is equal to 1/2, because I'll substitute 2 for the period, times, here we'll get t evaluator from 0 to 1, and here that will be minus, because we can factor out a minus here, t evaluated from 1 to 2. Well, this will be equal to 1/2 times, well, plug in the upper limit, we get 1, plug in the lower limit, we get 0, so this will be 1 minus, here we'll get 2 minus 1, and of course this will be equal to 1/2 times 1 minus 1, which is equal to 0. So in this case, a sub naught, the dc term, will be equal to 0. All right, next we'd like to find a sub n. So a sub n can be found by saying this is equal to 2 over the period times the integral. Now again, we'll have to split up into two integrals. The first one from 0 to 1 of the function 1 times the cosine of n omega t dt, and then plus the integral from 1 to 2 of the function of -1 times the cosine of n omega t dt, and let's put brackets around it because all of that is multiplied by 2/t. All right. Remember that omega is equal to pi, so we can write n times pi, and we can put the negative in front of here. So simplifying this becomes 2/t times the integral from 0 to 1 of the cosine of n pi t dt minus, because I bring the minus out here, the integral from 1 to 2 of the cosine of n pi t dt. And I want some brackets around it because I need to multiply all of that times 2/t. Now I'm ready to integrate. Remember that we need the proper differential n times pi, so we'll have to take that outside integral sign, but oh no, not that. What I'm saying is we need a proper differential, so we need to both multiply and divide by n pi in both cases right here. The derivative sign is the cosine, which means the integral of the cosine is the positive sign. This means that this is equal to, well, 2/t. Remember that the period is equal to 2. 2 divided by 2 is 1, so no longer need that. That's simplified. So now we have the 1/n times pi times the sine of n pi t from 0 to 1 minus, here we get 1/n times pi times the sine of n pi t. This would be from 1 to 2. Continuing, this is equal to So next, let's see here. When we plug in the upper limit, we get 1 times, because this will be 1, right? So we get 1 times pi, or 2 times pi, or 3 times pi, because n is, of course, an integer. So it'll be an integer number times pi. And an integer number times pi, and take the sign of that will always be 0. And plug in the lower limit, the sign of 0 will be 0 as well. So it looks like this term goes to 0. And here, same thing. When we plug in a 2 here for t, we get 2n pi. So this will always be an even number of pi. And when we plug in the lower limit, we get n times pi. In both cases, the sign of n times pi, regardless what n is, you'll always get 0. So this will go to 0 as well. So we really don't need to go on. We realize now that all the a sub n's equal 0. All right, so we can go ahead and get rid of this equal sign here. Next, we're going to find all the b sub n's. This again will be 2 over the period times, the brackets here, the integral from 0 to 1 of the function, which is equal to 1 between those two limits, times the sine of n omega t times dt. And here that would be plus, going from 1 to 2, minus 1 times the sine of n omega t dt, close the brackets. So notice that all of this multiplied times 2 over t. But again, this will be a 2, so 2 divided by 2 is 1. Don't need to do that. And the integral of the sine will be the negative cosine. So that means we end up with, this is equal to negative 1 over n times pi times the cosine of n pi times t, evaluated from 0 to 1. And here we get minus, well, a minus times a minus, which is a plus, 1 over n pi times the cosine of n pi times t, evaluated from 1 to 2. All right, how do we evaluate those? Well, if we plug in the upper limit, we get n times pi. If n is odd, we get pi times t, which is negative 1. And then when we plug in the lower limit, we subtract minus a positive 1, we get negative 2. Over here, well, that's only true when n is odd. When n is even, you plug in the upper limit, we get 2 pi, which is the cosine of 2 pi is 1. Plug in the lower limit, you get the cosine of 0 is 1. 1 minus 1 is 0. So again, like we saw in the previous example, this evaluated from 0 to 1 is only equal to a negative 2 if n is odd. If n is even, it's equal to 0. Over here, when we plug in the upper limit, we get 2 times n times pi. So regardless of what n is equal to, this always will be even, which means the cosine of this is equal to, always equal to 1. Plug in the lower limit. Let's see here. When the lower limit, the cosine of, this gets a little confusing, doesn't it? Let me just write it out and see what happens. All right, so anyway, here we have already discovered that this will be negative 2 times this, so this will be equal to 2 divided by n times pi, only for n equals odd. And here we're going to write plus 1 over n times pi, because this is a little bit more difficult to see, times. Plug in the upper limit, we get the cosine of 2n pi, minus, when plugging the lower limit, we get the cosine of n times pi. All right, let's see what we can make out here. If n is 1, we get the cosine of 2 pi, so let's write it like this. When n equals 1, this will be cosine of 2 pi, which is 1, minus, when this is 1, the cosine of 1 times pi, which is negative 1. So when n equals 1, 1 minus minus 1 is equal to 2. When n is equal to 2, we get, that will be 4 pi, which is 1, minus cosine of 2 pi, which is 1, which is 0. Similar thing here, just like in this portion. When n is odd, it's equal to 2. When n is even, it is equal to 0, which means that okay, that this is equal to 2 over n pi plus, this will be 2 over n pi because it'll be positive, which is 4 over n pi. All right, so now we realize that all the Biezen are equal to 4 over n pi, but n must be odd. Knowing that, we're now ready to plug all that information back into this equation. We're trying to find f of t. So we can say that f of t is equal to, notice a sub naught is equal to 0, so there's no dc term. All the a sub n's are equal to 0. We only have b sub n's. And the b sub n's are defined by 4 over n pi only when n is odd, which means that for n equals 1, we get 4 over pi, because n is 1, times the sine of n omega t. In this case, n will be 1, so it will be the sine of omega t. Plus, the next term will be when n is 3, because we can only take the odd ones. When n is equal to 3, we get 4 over 3 pi, 4 over 3 pi, times the sine of 3 omega t. And then the next one is when n is equal to 5. So there we get 4 over 5 pi times the sine of 5 omega t, and so forth. So here is the Fourier series of the original periodic function. Just like before, it's a function of sines. Notice in the last one we had 2 pi, 4 over 3 pi. I'm sorry, we had 2 over pi, 2 over 3 pi, 2 over 5 pi, and so forth. The only difference is that these are 4s instead of 2s, and we don't have the dc term because it is smack centered over the horizontal axis with half the function above and the other half function below with the same value, one above and one below the horizontal axis. So there's no dc term needed to settle it at the axis in the frequency domain, and since we have twice the value, it'll be 4 instead of 2 on each of the terms. So there's the function in the frequency domain expressed in terms of sines, expressing the original f of t, which is this periodic function right here. And that's how it's done.